getting close to the end of the course material, which yay for all of us. I don't know. Maybe I'll go ahead and put all the lectures up just so that seniors have access to them. But fortunately, most of this material is pretty straightforward to figure out, especially after today. Like after we get through today's material, you'll know like probably 99% of what you need to know for the rest of the course. So, hooray. So, we talked about process scheduling. Remember, we were talking about that last time. We had round-robin scheduling, which was nice, simple. Each process gets a chunk of time on the processor, and then, we preempted at the end of that time, although it could also yield the processor if it wanted to. So, basically, we have this issue of deciding who runs next, and this is all part of the same picture. Okay? I think the number one thing I want to say on the first chunk is that fairness is really important. We want to make sure that there's always an upper bound on the amount of time before a process gets the processor. Okay, that's really important, and it's easy to design systems carelessly in which fairness becomes a problem. And in fact, there's numerous examples of this. I'm going to tell you a little bit about this just because I know it's not going to be on the final. It's one of my favorite final problems. Mars Pathfinder was launched in like 94, I think it was. That was when I was graduating from high school. And the damn thing was resetting all the time because there was a fairness issue in the scheduling of the processes on that system. Okay, so they had to fix something. That was not JPL NASA's finest moment, but fortunately they were able to figure out a fix relatively quickly. So you have examples like that. Fairness can easily, be lost if you have a poor system design. Okay. Also, this is something that I wanted to mention. I've told you that context switches are about 20,000 clocks. You can think of them as being about that amount of time. So typically they're going to be on the order of 5 to 10 microseconds. And so I wanted to go through the things that happen in a context switch, and really we could revisit this in a couple of lectures after we finish talking about the material today and next time. But there's a lot of things that happen. First of all, you have interrupt dispatch has to occur. All right, so the process is interrupted via exceptional control flow. Remember all the steps in that. If we're in user mode, we have to switch to kernel mode. That means we're switching stacks. We've got to enter into the kernel. That means we're saving the process's context. We're doing a lot of things. Okay. So switch from process code to kernel code. There's a little bit, there's maybe like 20, 30, 40 instructions that are always run when you enter into the kernel that does this stuff automatically. Okay. So the kernel saves the process's context into the process control block or whatever kind of struct is used for that operating system implementation. We're going to presume that this is not something handled within the kernel, so we're just going to immediately dispatch to another process. And so the kernel has to run the scheduler, and ideally this goes really fast. Most operating system kernels do this job really quickly, but still you're going to have hundreds of instructions executing at the minimum to figure out who goes next. Then the kernel has to restore that process's context back onto the compute hardware. And then we return back from the kernel, so all of the stuff that we did to get into the kernel has to be undone. Pop all the context into registers, make sure that we've configured memory properly so that the new process can see its memory, and then we have to change back to the stack in user mode. So you can see that all of this stuff takes time. There's even other things that we haven't talked about yet that also add to the time of this. Because if you looked at this, you might say, well, that only seems like a few thousand instructions at most. And you'd probably be right. But the thing is that there's other things that also make this costly. And it's the infrastructure, the machinery from getting from user mode into kernel mode, back to user mode, and then some of the other details that we haven't talked about yet. Okay, but work. We don't like context switches. Context switches are basically time we're not doing useful work, so we'd like to minimize the number of context switches. In fact, there was this really interesting issue that I remember very distinctly when I was, one of my first internships, well, in fact, it was my first internship as an undergraduate, was at Microsoft working on Outlook, and the thing about Outlook, I mean, it was Outlook 97, so of course it was a desktop application at that point. It wasn't some service available on the web. And my mentor had the unenviable task of figuring out why Outlook was context switching so much. And so, obviously, if you're spending time context switching, you're not doing useful work. And so he wanted to get that way down. Okay? So anyway, resume executing the next process. Okay. So just keep that in mind when you see questions about context switches. They're good to avoid. It's really nice to try to minimize the amount of cost that you're incurring there. Now, processes can exhibit a wide variety of behaviors. We talked a little bit about that last time. Remember, we had the whole like prime number calculator, my text editor, video player, and I can't remember. There was one other one, but I can't remember what it is off the top of my head. Maybe a web browser. So they all have different ways of using the processor in the system, and we also have the additional complication that programs can change behavior over time. So we talked about round-robin scheduling. We talked about shortest jobs first. Remember, one of these was really nice for interactive processes. One of them was much more exciting to compute-intensive processes because they knew that they would get a nice large time slice without any interruptions. Okay? If we have a situation where all the processes or all the various concurrent things going on have the same general behavior, like they're all I/O intensive or they're all compute intensive, then it becomes a lot easier to design a scheduler. If I had a situation where I had a system that was just doing batch processing, so I know that most things are going to be compute intensive, but every once in a while they'll need to do I/O, it's really easy to design a system that does that. I don't care about user interactivity. I don't care if an event goes off and it's 5 seconds before I respond to it. But any user that had that happen to their system would probably throw it out the window. So you have to, when you have these mixed considerations, that's where it really becomes challenging to design a scheduler for that system. Okay? All right, yeah, so we need to balance the needs of these different kinds of processes. And in fact, you'll probably notice that anybody who gets an old cell phone or anything like that where the interactivity starts to drop off because the processor's running too slow or it's got too many things to do before it can get around to responding to that user input, it starts to get really annoying to use that device. And so you can imagine most of the devices we use have to think about this very carefully. Linux, for example, has this massive benchmark that they run to make sure that the scheduler will handle interactive processes effectively without generating too many context switches for compute-intensive ones. They have to test this stuff, make sure that things behave well. Now, real-time processes. We didn't talk about real-time processes yet, but typically these are deadline-driven pieces of software. So the video playback may say, I really would love to get the processor every 20 milliseconds or something like that. It's going to tell the operating system kernel, that's how often I want the processor. Okay. Tends to be cyclic, and fortunately, if things are going well, then they aren't going to be using the CPU for very long. So they're going to try to draw that next frame as quickly as possible, output the next audio sample to the audio hardware, and then they're going to go back to waiting for the next thing to happen. So there's various details. Like I say here, when is the deadline for each process? Now this is kind of an interesting question because the deadline is when the task needs to be completed. But that's not the whole picture because it's going to take some time to complete that task. So we can use the amount of time that we need to complete the task and the time that we have to be finished to figure out when we have to start by. Okay? And so then what we can do is we can just figure out which process is in greatest danger of missing its deadline. And you might notice here that this is a priority-based thing. Basically, we're looking at all the real-time processes, and we're picking the one that's in greatest danger of missing its deadline. And so there's a dynamic prioritization going on here, which is actually a really curious thing. We talk about this again in 124. It's absolutely fascinating. It turns out that this is able to maximally utilize the processor, this scheduling approach. There's another one, if you have static prioritization, where, for example, whatever the period length is, the shorter the period length, the higher the priority, that is not able to actually maximally utilize the processor. It's this interesting result that if you have too many processes, you can't actually maximally utilize the processor. But this one can. Okay. Let me see, what else did I want to say about this? I do say here that the scheduler can estimate several values. That's not really true. Because if you think about it, it's a lot easier if the kernel was told by the program, I need to meet this deadline. In fact, that's probably what a video player would want to do, is say, I need to hit this deadline. Okay. But the nice thing is that the kernel can estimate the runtime, because it can watch every single time the process runs. It can say, how long do you hold the CPU before you yield it? And so it can estimate the runtime. As long as it knows the deadline time, then it can go ahead and start tuning to the process's needs relatively easily. Okay, so there's some of this stuff it's best to be told. Some of it you can actually figure out on your own. Okay, any questions about this? Yes?
So what do you mean by maximally utilizing the processor?
What I mean is that if I have a real-time process that wants to, like let's say that 40% of the CPU cycles, it needs to use those. 40% of the CPU cycles. And then you have another one that wants 50% of the CPU cycles, and they both have real-time needs. Well, 40% plus 50% is 90%. Clearly, that should be schedulable, right? So it turns out that in a real-time scheduler with static priorities, you can't always schedule all of the real-time processes, even if the CPU utilization, the total CPU utilization, adds up to less than 100%, which is weird. But there's some mathematical formula. What is it called? Oh, I don't remember what it's called, so I can't tell you what to look up. But there were actually, I think there was a guy at MIT and a guy at JPL who worked on a research paper, and they proved this. It was really quite remarkable. But yeah, if you have dynamic prioritization, which you have here, then you can maximally utilize the CPU. If the sum of the CPU utilizations of all the real-time processes adds up to 100% or less, you can schedule it, which is really cool. Okay? Again, take 124 if you want to learn more about that. What else did I want to say? I don't think there's anything else to say about this. Are there any questions? We don't spend a lot of time talking about real-time processes in this class. So, in fact, this is the last slide you'll ever see anything about it. Okay, let's see. So, we have ideas about how to schedule these different kinds of processes. But you can see that each one is sort of has its own special needs. And so we need to make sure that each kind of process is handled in a nice, proper way to make the overall system behavior good. So interactive processes should run at a high priority. They should need a small time slice because that should be all, you press a key, it shouldn't take a lot of time to process that key press. So a well-behaved interactive process can be expected to become I/O bound quickly. Then you have compute-intensive tasks. They should run at a low priority so they don't interfere with interactivity. That would be really bad if they ran at a high priority. But we want to give them as long a time slice as possible. So as long as nothing more important happens, we want that compute-intensive process to have a lot of time on the processor. And then real-time tasks are probably going to need to be the highest priority. Or if not the highest priority, a really high priority, so that they can always be sure to hit their deadlines. Maybe you even want them to preempt interactive processes as far as prioritization is concerned. Okay. So we'll take all of these pieces and we'll figure out a way of assembling them together into a general purpose scheduler. It turns out that the approach that I'm going to describe here is used almost universally. It's really neat. So we have this concept of a multi-level feedback queue. Okay? And it turns out that this approach, like I was saying, is used in the vast majority of operating system implementations, with the notable exception of Linux, which uses a very crazy and different kind of scheduler. Okay. OS X has a similar idea, but it's a little different. So we're going to kind of ignore that one as well. We talk about those in 124 because that's where it's much more relevant. But here's the idea. We're going to have multiple queues. Processes will be assigned to a queue based on a couple of things. We're going to assign them to a queue based on their needs, and we're going to assign them to a queue based on their behavior. Okay, that's the whole idea that's captured in this notion, this name, multi-level feedback queue. We look at the behavior, we look at the needs, and we assign processes to a queue. Okay? Queues have their own time slices. Okay? So I can say this is the 5 millisecond queue, this is the 30 millisecond queue. And then I may also have my own scheduling algorithm for a particular queue. For example, if it's a queue where I stick real-time processes. Okay, clearly, I don't want to use round robin for real-time. That would be really lame and stupid. Okay? And so what I can do is, based on the observed process behavior, I will move it to a different queue as the behavior of the process would seem to dictate. Okay? And so the neat thing about this is that it ends up spreading the processes out into categories based on their behavior. So you quickly identify which processes are interactive. How do you know? Well, it blocks or it yields very rapidly. Okay, I block on I/O because I'm waiting for the next key press, and I use the processor for a really short time. Well, I can observe that behavior and move the process into a queue based on that. It never blocks because it's just churning on the CPU. It's my prime number calculator. Okay, well that one gets preempted all the time. So I can quickly identify based on the observed behavior the kind of process it is. And the neat thing is, because process behavior may change, I can still observe that, then I can go ahead and move it over time so I can adapt to a change in behavior. Okay, here's some example queues, 5 millisecond, 15 millisecond, and 30 millisecond time slices. And we're going to keep it simple. We're just going to do a first come, first serve scheduler here. Yeah, I mean, you can actually think of this as being round robin within each queue. Just want to make sure I didn't steer you all wrong. The general rules are, you always put the new process into the highest priority queue. Now, again, this may be based on its category. If the process announces to the OS kernel, I'm real time, then it may go into a different collection of queues. And if it just says, I'm a normal process, so it would go into the queues for normal processes. But you go ahead and put it into the highest priority queue. And then you watch it. You give it the CPU. What happens? Well, maybe the timer ticks off because you put it in Q1 and 5 milliseconds goes by. Process hasn't yield blocked or terminated, so we go ahead and say you are now demoted to the next queue level. So it ends up in Q2. Okay. If the process is going to block or yield, remember, those are the two main things. I mean, it's still sticking around. If it terminates, we don't care because it's gone away. But if it blocks or yields, then we say, well, you're a good process. You can stay in the queue that you were in. Okay? So it goes ahead and goes to the end of its queue. If a process behaves very well, and so it's blocking and yielding with less time than the next higher level queue requires, then maybe you can even promote it. So you can see that quickly you can move a process based on these kinds of rules. Are there any questions? Yes?
How many queues are there on typical systems?
That is a really good question. How many queues are there typically? It turns out that there's a lot of ways you can design these systems. And so I have some statistics later on in this slide deck. Hopefully I remember them. But you'll have operating systems with less than 20. And you'll have operating systems with less than 200. And in 124, when you implement multi-level feedback queues, you can actually implement the same thing in a single queue and just order things based on some prioritization, which is just a representation of which queue it would be in. Okay, so you can do this in numerous different ways, it turns out. Okay, Windows, as an example, only has 16. If I remember correctly, 16 or 32. We'll see it when we get to the slide. Okay. Whereas older Unix systems have a lot. Okay, any other questions? All right. Let's see, yeah, so this is great because processes will quickly be categorized based on their behavior. Now here's the other thing. Remember that we want to prioritize interactive processes. We don't know that it's an interactive process, except it's acting like one. It's kind of like duck typing. You've probably heard of this kind of concept before. It walks like a duck. It quacks like a duck. Well, if you have a process that ends up in the queue with a short time slice and it's getting blocked or yielding all the time, so it's going to the same queue, probably is an interactive process. So let's make sure that the queue with the smaller time slice has a higher priority. Okay? And then you just sort of say that the lower the priority, the longer the time slice, and so you just go through the queues in that kind of order. Okay? So basically what we do is we look at the ones that are in the highest priority queue with the shortest time slice, we do those. Eventually all of those will block, presumably. Now this is kind of an interesting issue. If it yields, it'll still be ready, so it may go to the back of its queue, and then it can run again. But eventually it should become blocked, and then we'll actually move it to some blocked queue. And so now that Q1 is going to be empty. So we go to Q2, and we run the ready processes there. And each one gets a chance on the CPU. It runs till it's blocked, then it gets moved to some blocked queue. Obviously, when one of those things becomes unblocked, it has to come back to the ready queue it was in. Okay? But you can just go through this, and eventually you get to the lowest priority queue where things are basically never blocking because they just love the CPU. They love spending as much time on the CPU as possible. So they just run till they're preempted. They go to the back of the line. Somebody else runs, and that just keeps happening. Those compute-intensive processes get all the luxurious time that they want on the processor until one of those higher priority processes becomes unblocked and can run again. Does that make sense? That's the idea behind multi-level feedback queues. Very powerful, generalized algorithm for solving this kind of a problem. Okay? I love it. It's cool. There's some really weird, badass scheduling algorithms that, Linux is really kind of on the bleeding edge of these things. I wish we had time to talk. We kind of do, because we have extra lectures at the end of the class, but we spend a lot of time talking about it 124 as well. Okay, so these were the queues, blah, blah, blah. Yeah, so the way to think about this is you've got Q1. Those processes have CPU bursts that are 0 to 5 milliseconds in length. And then Q2 is going to have processes with CPU bursts that are 5 to 15 milliseconds. And then Q3 is going to be 15 to 30. Okay, does that make sense? Well, let's say 15 or more, because remember, preemption is a thing. Okay? Easy peasy, right? Let's see. Now, typically we need to have different scheduling algorithms for different ranges of these queues because we have real-time processes. Like every OS is going to, any OS worth its salt is what I should say, is probably going to want to have support for real-time processes because people love watching media or listening to media. And so you need to have some way of supporting that in your OS so that playback doesn't suck, right? And if you think about like a PlayStation or a DVR or a DVD player or anything like that, like my little Roku at home, all of those things, like practically all they do is playback. So they have to have some kind of real-time scheduling support in the operating system scheduler, okay? So you'll have a slightly different set of queues with their own scheduling algorithms. And so this is the numbers. Let's see how well Donnie remembered these details. So yeah, NT-based systems, you have 32 queues, basically, 32 levels, half of them devoted to real-time. Okay, there's a couple of other categories on Windows. There's like system and real-time, and then there's normal. And I think real-time can even preempt system stuff. So, they make sure that real-time is good. Linux up to a certain level was, and then I also used to have like Solaris. Solaris would have like 250 queues, but who cares about Solaris, right? I don't know if any of you have even ever run Solaris. Anybody? Nope. Yeah, see, that's the thing. Used to be all over the place when I was an undergrad. Now sun is gone. Yeah.
How do the nice levels in Linux correspond to these levels?
That's a good question. I don't know exactly what the mapping of nice levels was to these various queues. Basically, if it's anything like the BSD scheduler, the older BSD scheduler, then the niceness of a process was used as part of a calculation along with the estimated CPU burst length, and that would end up with a prioritization. And then processes could just be sorted on their priority. And so nice was like an extra knob that the user could use to move a process to a much lower priority. So like I was saying, just because you see this thing saying that there's 140 levels doesn't mean that there's actually 140 linked lists with 140 head pointers and 140 tail pointers and all of that. You can do it in a single queue, reasonably easily as well. Kind of depends on the way the OS is designed. Yeah, and Linux has gotten so wild in the way that it does. Oh, it's a really cool scheduling algorithm that Linux uses now. It's called a stride scheduler. It's really cool. Look it up sometime. Again, that's not going to be on the final exam, so look it up. Okay, so the process API, you can see, remember all those details. They're pretty straightforward. Remember fork, signal for registering signal handlers, kill for sending signals, wait for finding out if a child's terminated, exit to terminate. Really simple stuff, right? I mean, it's like I can memorize the API. It's really straightforward. And then you have all of your long-running system calls, read, write, seek. What else? I'm trying to think of other. Well, seek, it can actually go really fast because it doesn't involve disk I/O. Changing directories, all that kind of stuff. You're interacting with an I/O device, so those will cause context switches. It's really easy to understand the UNIX process model. That's why we like teaching it. Okay? But the implementation can get quite sophisticated depending on all of these kinds of needs. Okay? So, particularly in the context of process behaviors. Okay? So, any questions about any of this? You can see that I kind of don't care about my rah-rah summary slide, but hey, there it is. Okay, but I do want to go to this one. This is actually, I really like this slide. We've been talking about developing a process abstraction. This is kind of cool, virtualize the processor. Now we have different programs that can use the single processor. Obviously, time slicing it, they don't use it at the same time because they can't. Okay? But we have this cool abstraction that we're developing. And so we asked ourselves the question, well, who manages the processes? And so we said, well, how about a control process? We need to distinguish between what the control process can do and the user processes. So we have operating modes. Yay, hardware. That takes care of us. What state information do we manage for processes, and how do we manage it? Well, we have registers. We understand how to do that. All of you, it's really interesting, but the way that you're solving the problem of concurrency in assignment 6, and then it's already solved for you in assignment 7, you're starting to do other things in assignment 7. That's the way operating system kernels do it. You call into the kernel, you get a kernel stack for that kernel thread, and the registers are pushed onto the stack. That's literally how your OS is doing it. You switch to another process, well, that's got its own stack. And guess what happens? First thing, we pop the registers off of that stack. Okay? That's literally how it works. So anyway, we know how to handle registers, we know how to handle flags, but we haven't talked about program memory. That's a giant problem that we haven't sorted out yet. Okay, well, what about interrupting a process? We need preemption. Okay, so we have a solution for that now. We have this hardware exceptional control flow mechanism called interrupts. Okay, something on the hardware goes ding, and it transfers control to somewhere else. How do we choose which process should run next? Well, we have an idea about how to do that as well. One of the things that makes me slightly sad about CS24 is you never get to implement a scheduling algorithm. Okay, you do round robin. In fact, that's what 6 does, and that's what 7 does. You just implement round robin, which makes me a little sad, but that's the way it is. Okay, life goes on. Take 124, you'll get to do it in assignment 3, and you'll be sad. So you do get 2 weeks, but it still make you sad. So anyway, but you can see that we kind of have this gaping hole. Program memory. We don't know what to do about program memory. Okay? So what do? We wanted to isolate address spaces. Remember, we had this stupid picture with like a magic box, and it had the rest of the box, and the control process could see everything, but the program could only see inside the box. Well, how do we actually implement that so it doesn't suck? Right? That's the next thing we have to figure out. And how do we provide faster context switches? Because remember, our sketch so far has been copy junk out of the box somewhere else, and then copy other stuff back to the box. That sucks. That's a terrible way of doing things. We need a better way. Okay? Here's some other questions that we could ask ourselves. Like if we want to have an OS that's cool. Okay? How do we provide access to the kernel and shared libraries in an efficient and uniform way? Like libc. You guys have been using libc all term, whether you know it or not. That sucker has to be loaded into memory for every one of your programs. Why duplicate the memory usage for every one of the programs using it, since virtually all programs use it? How do we let processes share memory and coordinate with each other? Okay, so those are some examples. We'll even have other questions that we'd like to ask as well. Okay, so this was the approach. Remember I was saying we had this box and it was really cool when we first started talking about it. It was like the best thing ever. But now we realize that it has some lameness as well. Okay? So context switch was, I interrupt the running program, I copy its context somewhere, copy another program's context back, and then start running the new program. Okay? Remember, this was the sketch of how it would work. The larger the program is, the slower context switch is, because I have all this data to move around. Okay? So, yeah, like I was saying, copying programs is slow. In fact, you remember how I mentioned that fork in Unix, all it does is it duplicates the process control block? And we didn't really have good ways, I wasn't alive back then, but they didn't have a good way of implementing this stuff yet. And so they would actually duplicate the entire context. So forking was really slow. It would take like a second or two to fork a large program because of all the copying going on. You remember that memory was slower, programs were smaller, but still they found a way for it to suck. Okay? So basically we also have another constraint right now that all of our processes have to fit into memory. What we're saying here is that we can't overcommit the amount of memory that we have. We can't say, I'm going to load 20 programs that need 10 gigs of memory if I only have 2 gigs of memory. Okay? Maybe you didn't realize that, but all of your computers overcommit memory all the time. It's like our banking system. Okay? You expect a lot of people are going to leave money in the bank all the time. Okay? So, we've kind of been talking about program and memory usage in a concept that we consider to be like physical addressing. I have a program. It contains an address. It runs that instruction that emits the address from the processor, and that's a physical address. It corresponds to a physical location in memory. Okay, so main memory is fixed. We'll say it's capital M, contiguous bytes. Okay, so the instruction contains an address. It emits that address. That is a physical address. We've been talking about it this way all term, whether you realize that or not. We've just kind of assumed. We didn't probably think very carefully about what these addresses are. Okay. So what we'd like to do is solve the problem by adding another level of indirection, as per usual. So what we're going to do instead is have instructions use virtual addresses. The addresses that they emit are not actually going to be the same address that hits the memory cells. We're going to have a translation that goes on between the two. And so we're going to turn virtual addresses into physical addresses. So we end up with a scheme like this. So instead of saying, the instruction has address alpha, well, instead of just saying we're going to access memory at address alpha, which has kind of been our abstraction all the way up to this point, instead what we're going to do is use that address alpha and put it through a mapping table. And then whatever the mapping table says, we'll use that address. So now that mapping table becomes a level of indirection between the instruction addresses and main memory addresses. Okay? You've already done this before. Remember homework 3, you had the allocator, the explicit allocator. When I hand back stuff, it's an address into the memory pool. Then you did homework 4. The addresses that came back were entries into the reference table. And then you would access things indirectly. We're doing the same thing with memory. Okay, this is why, there's that saying, all programs in computer science can be solved by adding another level of indirection. This is a clear, obvious example of this. Okay, now we don't want to map every single address, because remember, on x86-64, we've got 2 to the 48 different addresses. That would suck. right? We don't want to have a humongous table. So since we see that the table would be too large, and since we typically have programs that want to access memory in chunks because they want to achieve good locality, remember we have cache lines, those are 64 bytes. Well, maybe we should do this address mapping thing on some kind of block level. And so memory is divided into pages of some size that is a power of 2. So you can go ahead and start internalizing in your brains right now 4 kilobytes, or kibibytes if you will, but 4096 bytes is the size of a page on the x86 processor family architecture. Okay, so you choose a page size much larger than 1 byte or 1 word. Okay, and then you map virtual pages to physical pages. Okay, and so the mapping, that table becomes a page table. That's what we call it, is a page table. And the page table entry says which physical page each virtual page is stored in. Okay, that's the scheme. This is the plan that we're going to try to implement. Okay, so we have this physical address space, and you guys are implementing something like hinky and kind of close to that in assignment 8. You can sort of at least see a few of the details. It's not the best assignment, but it's okay. It's pretty good. It's definitely better than it used to be, so that's cool. But anyway, you have this physical address space that's of size capital M bytes, and then you also have a virtual address space of capital N bytes. Okay. And right now we're going to keep it simple. We're going to say that both of these are a power of 2 in size, so that we know how many address bits we're dealing with. We're also going to make the further assumption that M and N are the same size themselves, because that also simplifies life. So we're going to assume that capital M and capital N are the same. They're also a power of 2, so lowercase m and lowercase n are also the same. And so then what we have is this need to translate virtual addresses, because our programs, let me put it this way. The programs are operating entirely within a fabricated construct. It's like the program is living in the matrix, right? And it only knows about virtual addresses. It has no concept that there's such a thing as a physical address. The only thing in the system that really cares about physical addresses is the kernel, because it's the thing that manages these mappings. Okay? So the program just emits virtual addresses, and then we have to translate those through this page table into physical addresses. And that all happens from the CPU on out. The program doesn't have any clue that this is going on. Okay? So like I say, the address translation in software would be slow. In fact, you will see an example of that in assignment 8. So we have a special hardware component that is on the processor. It's called the memory management unit. It does a lot of things, in fact. It also is where we can enforce memory access permission. So if we say that memory is read-only, the MMU enforces that it's read-only. If you say that part of memory is not executable, and the MMU sees an access for loading an instruction, it'll freak out. Okay? The MMU can fire various faults to say these problems are occurring. Okay? But the MMU is the hardware component on the processor that does this address translation. So you can see that you can give the MMU a page table. So you just say to the MMU, this is the mapping that I want to follow. And the MMU automatically does the virtual to physical address translation for the program. Okay, everybody got that? You can probably imagine that the address translation configuration cannot be changed by the program. That's protected because the operating system kernel should be the only thing allowed to change it. Otherwise, writing rootkits and other malicious software would be super easy. I just go in, say I want to see everyone's data, and the OS says, okay, and then, everybody's data is lost, right? So thankfully, the hardware can only be accessed from protected mode. Okay? Here's how the mapping occurs. Remember, we have this virtual address. It's n bits. Now remember that the page size is a power of 2. So some of those bits, the rightmost bits, are going to be used to figure out an offset within that block. That part's the easy part. Okay? So you have the virtual page offset, where lowercase p is dictated by the page size. The rest of the bits tell you what virtual page you're within. Okay? So it's a virtual page number. Physical address, you have the physical page offset. You can imagine the physical page offset will be identical because the pages in virtual addressing and physical addressing are the same size. We don't want to be crazy. And then you have a physical page number. So you can imagine we have the two parts of the virtual address. We know how to get the physical page offset because it's just the same as the virtual page offset. We just need to figure out how to get the physical page number given the virtual page number. Okay? So that's what the page table does. And it's a super easy, simple mapping mechanism. We use the virtual page number as an index. We just look at the appropriate index in the page table. The entry at that index is the physical page number that the virtual page is stored at. That's all it is. It is literally that simple. So you take the virtual page number, do an array index, or array access, you get the physical page number out, you're done. Okay? Any questions? Now there's a whole bunch of reasons why this isn't the whole picture. Okay? Part of the issue is that if you were to implement this on a 48-bit address space, the page table would be like, I can't remember. I think it's, I want to say 512 gigabytes in size. That can't be right. Maybe it's 512 megabytes. It's monstrous. Monstrously. I think it might be 512 gigabytes. Ugh, terrible. Okay? So, we need a way of making this much more efficient. Okay? But this is the concept. It's so easy. Okay? All right. Now, how do we know where the page table is? What do we use to control the mapping? There's a special register on the processor, again, only accessible in protected mode, and that's the register that holds the address of the page table. Okay. Don't quote me on this. I'm pretty sure it's true. But this is one of the few places that the OS kernel has to be thinking about physical addresses, because obviously the page table is going to live at some physical address. That part is not going to be behind the physical to virtual address mapping. So that's one of the few places the OS kernel has to think about physical addresses. All right? But you just change the page table base register and suddenly the view of memory changes. Let me show you an example. So now, instead of having little boxes and we copy boxes around and things like that, now we've divided main memory up into pages. Okay, all of the boxes on the far right are physical pages. And then each one of our programs running, so each one of our processes, has its own page table saying, these are the physical pages I'm aware of, and these are the virtual addresses that the physical pages live at. Okay? And so then the processor has its page table base register. And so, what do I do when I want to context switch? Well, I still have to save and restore the register state. That's always going to be a thing. Like that, I always have to do that. But to change the view of memory, all I have to do is change what the page table base register is pointing at. I just change it to another page table, and now I have that process's view of memory. Everybody see that? Any questions? This is so freaking cool. I love it. There's even more awesome and neat things you can do with this that we don't even talk about on CS24. Okay? But this is the idea. This is how your computer is able to switch between programs. Now, I wanted to mention something. I said that this is still going to be like a 20,000 clock-ish operation. Okay? That's using this mechanism. You can imagine that doing a context switch with an old school, let's just copy tons of memory around, would be much, much slower. But this is part of how we can say it's always going to be an approximately constant number of clocks, even though different programs may have different address space sizes, virtual address space sizes. Okay? Everybody got that? Okay, let's see. So virtual memory. What other things can we do with this? Well, let's say that our instant messaging client, I don't know if people even use those anymore because your web browser is like all of these things now, except for the kernel. So you have your kernel and your web browser. That's all you have now. But basically the physical memory layout of a program no longer has to be contiguous. Why does it care? The virtual address space can be contiguous, but the physical pages can be anywhere because you just point the page table at the appropriate physical pages. It doesn't care where those things live. Okay? So if the IM client needed more memory, Well, that's real easy. We just go into that process's page table, add a few more page table entries saying, here are 2 new physical pages that your program can now use. And now it has 8 kilobytes more space. Okay. So when your heap needs to grow, okay, because in assignment 3 you didn't implement a growable heap, you had a fixed size heap. You run out of memory, you're sad. Well, maybe you're not sad, but the tester is sad. So no biggie, right? But in real life, when you have a heap, you're given a certain amount of space, and then when that heap runs out, the runtime talks to the kernel and says, hey, I need more memory. My process is using a lot of memory. Can I please have more memory? And the OS kernel will come back and say, here are more physical pages. Go for it. Okay? So that's the kind of thing happening behind the scenes. All right. Any questions? All right. It gets even more sophisticated than that, but we'll talk about that next time because I don't want to blow you all away. What if I want 2 programs to collaborate with each other? Remember that in general, the default behavior is we're going to have an impenetrable barrier between processes. So they cannot muck with each other. Okay? Now, obviously, they can touch each other's files and junk like that, unless the OS is designed with permissions and so forth. But in general, processes have an impenetrable barrier between them. Well, if both sides say, you know what would be really cool is if we could actually access the same memory for whatever reason. Okay? Then you can arrange that because you just have their page tables point to the same physical pages. Okay? Now we can start doing cool things like have shared libraries like libc, which, like I said, virtually every program that runs on your computer uses libc. So why not load it once into a couple of physical pages, and then when any program wants to use it, we'll just point virtual page entries, virtual page table entries to those physical pages, and then they get access to libc. Okay? So that's the idea behind a shared library. If I even want to be crazier and allow the programs to write to each other's memory, so one program writes and the other program sees it, well, then I can do that as well, using a shared memory abstraction, which again, most OSs support at least one, typically 2 or more different ways of sharing memory mappings between programs. Okay, any questions? It's the idea. All right, so you can see that all we did was we made this one little change. Let's have a level of indirection. And all of a sudden, we get all this power, all this cool stuff. So we get faster context switches, yay, go us. Processes can now have isolated virtual address spaces, which is cool, right? Because I can run 2 GCCs at the same time without, both of them think they have, sole access to memory. They have no clue that, there's actually a page table sitting in between and their physical pages are not overlapping, but their virtual addresses can, of course, overlap. All cool, right? So that's handled in hardware. Physical memory layout doesn't have to be contiguous. Go us. There's only one place where we care about physical addresses, and it tends to be, you guys remember that DMA concept that we talked about with interrupts, where I want my disk controller to write to memory, or let's say I'm sampling audio, and so the sound card needs to write to memory. That tends to be the only time where you care about physical addresses, because these devices can't necessarily access all of the address space. And so the OS has to know about that, but programs thankfully don't. Okay? So this is all cool. The issue is the one that I mentioned before. We still have this limited resource of physical memory. And so that becomes a cap. Even if a process isn't doing anything, it's blocked or whatever, well, I still can't commit its memory to someone else. Okay? So this is the remaining issue that we have to solve. So let me see. I might not always be using all of its memory. So next time what we're going... Oh, yes, question?
So if the program's physical memory layout isn't contiguous, does that hurt the locality of the program?
So this is an interesting question. Does if a program's memory is not physically contiguous, does that hurt locality? Fortunately, it does not, because the cache lines always divide evenly into a page. And they make sure, pages are a power of 2, cache lines are a power of 2. And there's a really complicated topic that we never broach in this class, which is, do the hardware caches use physical addresses or virtual addresses, or some combination thereof? And all of that works together in a very sophisticated way to make sure that you still get to benefit from locality of access, even though you have this virtual memory concept underlying it. Yeah, so it's very, very well designed. It's a really powerful. It's beyond my ability to explain at this point. Anyway, any other questions quickly? All right, so what we're going to do next time is we're going to figure out how to work this into the memory hierarchy so that we can start using DRAM as a cache for the disk. So that'll be our discussion next time.